In this video series, we will completely hunt down the physics of wave nature and then begin to hunt other magnificent areas of physics. Best of luck to everyone. In previous videos, we hunted down the oscillatory motion, which is the fundamental building block of the wave mechanism. Now, let's observe wave phenomena in nature and first hunt down the properties of waves before interpreting and solving the wave equation. A wave is a motion system formed by many oscillating systems being connected in a way that they affect each other. For example, the oscillations that create an electromagnetic wave are magnetic and electric fields. These fields influence each other over time to form an electromagnetic wave. In a water wave, each molecule oscillates, and due to the energy transferred through the bonds between molecules, other molecules are affected by these oscillations, creating the wave phenomenon. The wave you see is a wave traveling in the x direction while oscillating in the y direction. By examining the motion of this wave, let's hunt down its properties. First, we mentioned that a wave consists of multiple oscillations. Therefore, a wave possesses the properties of oscillatory motion. Let's recall these properties. Oscillatory motion has a frequency, which indicates how fast the oscillation occurs, and represents the number of complete oscillations per unit time. The oscillatory motion can stretch to a certain maximum value, known as the amplitude, which measures how far the oscillation can deviate from its equilibrium position. Another property is the phase. The phase describes the value of the oscillatory motion relative to its initial position. If two identical oscillation systems are out of sync, the difference is due to the phase property. Since a wave naturally inherits these properties from oscillation, it also has its own unique characteristics. Because a wave consists of many oscillation systems, the distance between two particles that are in the same phase one after another is defined as the wavelength. Therefore, the higher the frequency of the oscillation system, the shorter the wavelength. Because as oscillation speed increases, the distance between two particles in the same phase decreases. In fact, the wavelength represents the distance required for a complete wave to form. From this perspective, the reciprocal of the wavelength expresses how many waves exist in a unit distance. This quantity is called the wave number and is represented by k. Since a wave consists of many oscillation systems, the phase of an oscillation will appear to move forward. For example, if we track the crest of a wave, this crest will seem to move at a certain speed even though the oscillation system itself is not moving. This is called wave speed. Because wave speed represents the movement of an oscillation phase, it is determined by multiplying the wavelength, which represents the repetition of an oscillation phase, by the frequency, which represents how quickly the phase occurs. From this equation, it is clear that the speed of a wave is not affected by the speed of the source generating it. Thus, we can conclude that the wave speed is determined by the medium, and the source of the wave has no effect. Understanding the propagation direction, speed, and type of source of a wave is essential for comprehending its behavior. Therefore, a feature called the wavefront has been introduced to help describe wave behavior. A wavefront is a surface connecting points that are in the same phase of the wave, e.g., all at crests or troughs. Each point on the wavefront is at the same distance from the wave source. The distance between successive wavefronts corresponds to the wavelength. By examining the shape of the wavefront surface, waves can be classified as either spherical or planar. Spherical waves emitted from a point source typically form spherical wavefronts. Such a wave propagates uniformly in all directions, creating a spherical surface where each point is equidistant from the source. For planar wave, if the wave source is large and spreads waves over a wide area, or if waves are examined at a great distance, the wavefronts become planar. The medium in which the wave propagates can also cause the wavefront to be planar. These are the fundamental properties of waves. Based on these basic characteristics and the medium in which the wave exists, different types of waves have been observed. In nature, both oscillating particles and oscillating fields can generate waves. This is the first classification of waves. Waves that require particles to propagate are called mechanical waves. Waves that do not require particles to propagate, i.e., waves formed by fields, are called electromagnetic waves. Another classification is based on the relationship between particle motion and wave direction. If the oscillating particle's motion is perpendicular to the direction of wave propagation, it is called a transverse wave. If the oscillating particle's motion is parallel to the direction of wave propagation, it is called a longitudinal wave. All electromagnetic waves are transverse waves. This is because the oscillations of electric and magnetic fields must always be perpendicular to the wave's propagation direction. In mechanical waves, both types can exist separately or together within the same wave. For example, the sound waves that create music are mechanical longitudinal waves. The waves observed on the strings producing the sound in music are mechanical transverse waves. Both types of waves can be observed in surface waves near fluid systems. Now that we understand the nature of waves, their connection to oscillation, their properties, and their types, we can mathematically express and solve wave phenomena. In the previous video, we hunted down the wave equation. If we examine the behavior of oscillation systems forming a wave, the time-dependent derivative in this equation represents how each oscillation system changes over time, while the position-dependent derivative represents the oscillatory motion that forms the wave based on position. Therefore, solving these two partial derivatives separately is similar to solving simple harmonic motion. The final solution is the product of these individual solutions. First, we derive the general solution for harmonic motion as follows. Since our function now depends on both time and position, we need to include a position term. The frequency determines how many oscillations occur per unit time. So to find a similar measure for position, we use the wave number. The wave number represents how many oscillations exist per unit distance. By multiplying it with position, we obtain the number of oscillations in that distance, just as we did for frequency and time. This is an equation representing wave motion. The negative sign in the equation indicates that the oscillation changes in the opposite direction over time. Therefore, this equation describes a wave traveling in the positive direction, while the alternative solution describes a wave traveling in the negative direction. In this equation, omega represents the radial frequency of the wave, and k is the x component of the wave vector. Since we are considering a one-dimensional traveling wave, only the x component of the wave vector is relevant. A and b are the amplitudes of the wave, and their values depend on the conditions of the wave system. Now that we understand waves more closely, we can begin to explore what happens when waves enter different mediums or encounter obstacles or slits. The foundation of this exploration is Huygens Principle. Therefore, our next task is to understand this principle. In the next video, we will hunt down Huygens Principle.